Hello class, this is Mr. Sutton, and today we are going to be talking about parent functions and function transformations. What is a parent function? A parent function is the simplest version of a function that still satisfies the definition of that function. So you want to have that definition in your notes. The first parent function we're going to look at is the square root parent function. So that is this right here. This is what it looks like as a graph. This is the actual equation of the square root parent function. So it's the simplest version of that, meaning it is just a square root. So the function is we plug in a number, and the input is the number we're plugging in. The output is the square root of that number. So here are some key points to write down. 0, 0. You plug in 0. The square root of 0 is 0. 1, 1. You plug in 1. Square root of 1 is 1. So here's 0, 0. Here's 1, 1. And then 4, 2. You plug in 4. The square root of 4 is 2. So that would be up here. So if you are graphing this on your own, if you remember these points, that kind of gives you a guiding line for your function. And once we get into transformations as well, it's important to know these points because that is what we will be manipulating for the transformations. So you want to make sure you have all of this in your notes, the equation, the key points, and a sketch of the graph. Next is the quadratic parent function. This is what the graph looks like, parabola. This is what the equation looks like, f of x equals x squared. Here are your key points, 0, 0, this point right here, 1, 1, this point right here. And since this is a parabola, those points are mirrored on the other side. So then we have negative 1, 1, negative 1 squared is positive 1. And then next we have 2, 4, 2 squared is 4. And then that is mirrored on the other side as well. Negative 2 squared is also 4. So negative 2, 4. So you want to make sure you have this graph, this equation, and these key points in your notes. Next we have the absolute value parent function. Absolute value parent function looks like this V shape. This is the equation. It is just the absolute value of x. Key points, 0, 0, 1, 1. From this side of the graph, it looks just like a linear y equals x line. Difference is the left side of the graph is flipped up because as you plug in negative numbers, positive numbers come out. Negative 1, 1, absolute value of negative 1 is 1, and then 2, 2, this point right here, and then negative 2, 2. The absolute value of negative 2 is also 2. So you get this V shape. From these points, you should get that pattern, be able to draw it in your lines based off of that. Next, we have the cubic parent function. This is what the graph looks like. The right side of this graph kind of looks like the quadratic. If I did that, you might think this looks like a quadratic. Difference is the right side grows faster because this is cubic now, x to the third power instead of squared. So we have points 0, 0, 1, 1, and then 2 cubed goes to 8 instead of 4, right? So it's growing a lot faster. And a big difference between the cubic and the quadratic now is the left side of the graph, the quadratic, the negative numbers have positive outputs, but with the cubic, this left side flips down, and as you put in negative numbers are the output as well. You have negative 1 cubed is negative 1 as well, right? You have this point down here. And then negative 2 cubed is negative 8, which is off the graph, but would be down here somewhere. So with the cubic graph, that's one thing to note. As you plug in negative numbers, you have negative outputs as well. And so you get this S shape. So that's what the graph looks like. Here's the equation, and here are some key points to note. Next, we have the cube root parent function, which looks like this. Similar to the square root function, the right side is at least. We have 0, 0, 1, 1. But again, this is a little more extreme. This goes to the right faster than it goes up. So in the square root function, we have this point 4, 2. So it would look kind of like this. But that's not the case in the cube root function. The cube root of 4, if I plug in 4 into the cube root function, that's this point right here, which is at 1.5874. So if you take the cube root of 4, you get that point right here. So it's not growing as fast. We do have the next nice clean point is this 8 comma 2. So out here, where x equals 8, we would have that point 8 comma 2, which is off the graph here, but worth noting. Now, one big difference between the cube root and the square root is the left side of the graph. Now, if we go back to the square root graph, notice that there is nothing over here on the left side. That is because if you plug in negative numbers into a square root, you get a domain error. Try to take the square root of -1. It says domain error on your calculator. If you recall, that is an imaginary number. And the problem is we don't have imaginary numbers on this graph. So that is why we don't have any graph on the left side. But if we go to the cube root function, we do have a graph over here. That is because you can plug in negative numbers into a cube root. Cube root of -1 is -1. That's this point right here. Cube root of -8 is -2. That would be off the graph again. So some key differences there. Make sure that you have all of this in your notes. Next, we have the exponential parent function. Here is the equation here. F of x equals 2 to the x power. One thing to note here is that x is in the exponent. That is why it's the exponential parent function. And then your key points, 0, 1. This time we're not at the origin, because if you plug in 0 here, 2 to the 0 power is 1. Anything to the 0 power is 1. So that is one of our key points there. And then 1, 2, 2 to the first power is 2. So we have 1, 2. And then 2, 4, 2 to the second power is 4. So on the right side of this graph, it grows really fast because our exponent is getting bigger each time, so it's growing exponentially. The left side of this graph, as you start plugging in negative numbers into the exponent, this gets closer and closer to 0. Now, it does not pass this x-axis and go to the negative side of the y-axis. It just gets closer and closer to 0. You can try this. You can take 2 to the -100 power, and you will get a very small fraction, but it will not be a negative number. And the reason why that is, if you remember, negative exponents, like I said, 2 to -100, that moves your number here to the denominator. So that becomes 1/2 to the 100th power, right? So that means you have a really large number in the denominator, which means you're getting very, very close to 0. So that is what exponential parent function looks like. And that is our last parent function. So you want to make sure you have all the notes for those 6 parent functions down. Now here are your transformation rules. You want to take a second and make sure you have all of these written down. So I'm going to go ahead and talk through these. So f of x just represents your function. If you are adding something to that function and it's outside of the function, that is a vertical translation up that amount of units. If you are subtracting something outside of that function, that is a vertical translation down that amount of units. If you are adding something inside the function, that is a translation left that amount of units. If you are subtracting something inside the function, that is a translation right that amount of units. So I want to go through some examples just showing you what these mean. So for these examples, let's use f of x equals x squared. Let's use the quadratic because you're probably most familiar with that. So an example of f of x plus d, that would be like if I had, let's say I had my function g of x is x squared plus 5. So I'm adding that 5 outside of the function. My function is x squared. That's the parent function, x squared. And I'm adding 5 to that outside compared to this example down here. Let's say g of x equals x plus 5 squared. That is inside the function because the parent function is squared. So now I'm adding 5 inside of the square. So this would be a translation left 5 units versus this example up here is a translation up 5 units. So that is the distinction. This plus 5 is outside the function. This plus 5 is inside the function. All right. So parentheses are going to be your friend to help you determine these differences for a lot of these. I'm going to fill out some more examples here on the right side of this. So here are some more examples using the quadratic parent function. So here is subtraction outside of the function is down. Subtraction inside the function shifts right. Here is multiplying by a negative value outside the function. This is a reflection over the x-axis. Now note here that no parentheses indicates that this is outside of what is being squared. Sometimes you might see this with parentheses like that, or you might see it with no parentheses at all. So I think more commonly you'll see it with no parentheses at all. That means that this negative is not being squared. And then the negative inside the parentheses means it is being squared. That's a reflection over the y-axis. And then here, multiplied by an integer outside of the function is a vertical stretch. That's if the value is greater than 1. If it's a fraction between 0 and 1, that's vertical compression. So it's shrinking vertically. And then if you're multiplying by a value inside the function like this, that if it's greater than 1, horizontal compression. So like this. And then if it is a fraction between 0 and 1, that is horizontal stretch. And then this column here tells you how your coordinates change. So that is also worth noting. So like for this one, our coordinates would change from x comma y to x comma y plus 5 in this example. So every y value would increase by 5. All right, so make sure you have this table written down and think through what it all means. If you have any questions about anything on this table, let me know. This table is very useful for you to reference on your practice assignments and on your masteries. So let's look at some examples here. The graph of y equals f of x is the solid black graph below. So this right here, which is in this case our parent function, the quadratic parent function. Which function represents the dotted graph then? So for this one, we can see that this point right here, one of our key points, was shifted to the left 2 and then down 1. And we can also see that this point right here is also shifted to left 2 and down 1. So since they're both shifted to left 2 and down 1, that means there's no vertical or horizontal shrinking. This is just a shift. So we want to look back at our table. Left is when we add inside the function, and then down is when we subtract outside of the function. So that means we need to add 2 inside the function and subtract 1 outside the function. So this would be our answer here. Next example, f of x, this time is the absolute value parent function. So this key point right here, 0, 0, is being translated to the right 3 units. And then we have a reflection over the x-axis. So we look back at our table, and right is subtraction inside the function, and reflection over x-axis is negative outside the function. So that would have to be this one right here. Subtracting 3 inside the function and negative outside of the function. So now let's look at this example. Here, difference between this one and the previous one is f of x this time is not a parent function. It is some other absolute value function, but we're still calling it our original function here. So we got to figure out the transformation from this function to the dotted function, not from the parent function. So that is worth noting. So this point right here moves to this point right here. So we're shifting up 1, 2, 3, 4, and left 1, 2, 3. So that means we're adding 4 outside the function and adding 3 inside the function. So that would be this function right here, this equation. So now let's look at some examples where we're actually graphing in Delta Math. So here we have the cube root parent function, but we're subtracting 3, and this is inside the function. It's underneath the cube root, so that's inside the function. So that would be a shift right 3 units if you reference the table. So I'm going to go ahead and shift right, and it kind of locks into place. And we have no other transformations here, so all these other points should stay the same with respect to that point. So I'm going to go ahead and submit this. All right, good. And then here's another one. This is an exponential parent function. And here we're adding 2. This 2 is outside the function. For the exponential ones, for the exponential functions, adding inside the function means it's also in the exponent. So if you have x plus 2 as your exponent, that is inside the function, so that would be a shift left. But here, since we're adding 2 not in the exponent, that's outside the function, so that is a shift up. So that's what we have here. This is outside the function, so adding 2 outside the function is a shift up. So I'm going to move this whole thing up 2 units, and everything else is the same as our parent function. We have this 2 here, but that is part of the parent function, so that doesn't affect anything. So this should be our final answer here. Yep. So those were level 1. These are level 2 now, which I guess level 2 means that we have 2 transformations here. So here we have 2 translations. We have this plus 1 inside the function, so that is a shift left 1. So we're going to go left 1. And then we have this minus 3 outside the function, so that is a shift down 3. So we want to go down 3. And then everything else should be in the same respect to our original point. So let me go ahead and submit this. So here we have cubic function. We have this plus 1 inside the function. It's inside the part being cubed. So that means shift left. So you want to, again, reference your table on these. And then we have minus 1 outside the function, outside the part being cubed. So it's outside the function. So that is a shift down 1 unit. Oh, and I just realized I did not fully shift left 1 unit. I stopped at 1/2. So sometimes it won't lock in exactly where you want it to go. So make sure you do that properly. Yeah, so now I'm left 1. So now I want to shift down 1. All right. So now we're past the translations. Now we have other transformations. So the past 2 sections were only static shifts, left, right, up, and down. Now is when we get to reflections and some dilations. So this is our quadratic. First thing I notice here is we have a negative out in front. The negative is not being squared, so it is outside the function. So that is a reflection over the x-axis. So this is where we start to move the blue dots here. So the green one can stay where it's at for now, but we're going to move these blue dots down here, reflect them over the x-axis. And then the other thing is we're also multiplying by 2. So that is a vertical stretch. Since 2 is greater than 1, we're really multiplying by -2. But if you reference the table, it's the absolute value of that value. And so 2 is greater than 1. So that is a vertical stretch. And so what that means is for your coordinates, you multiply your y value by that value here. So we want to multiply our y values by -2 here. So if you think about our original y value, like this one is 1. So we want to bring 1 times this -2 is -2. So not only do we want to flip it down here, we also want to stretch it all the way down to -2. So this is what it says in the table on where we have the vertical stretch. For the coordinate part, it says xy goes to x a times y. So this is where this can come in handy. So you pick a point, like we picked that point right there, 1, 1. So our a value in this problem is -2, right? If you think about it in this form, f of x is that x squared, so a has to be -2. So our new coordinate, x stays the same. This part right here is 1 times our a value, -2. So our new coordinate is 1, -2. We reflected it down and we stretched it. So that is where this change to coordinate point column comes in handy on the table. So let's go ahead and split that. See, it says multiply y coordinates by -2. So we have a vertical dilation of -2. So now let's look at this one. We have this 1/8 out in front. So that would be vertical compression because 1/8 is between 0 and 1 and it's outside of the function. So that's vertical compression. And then we are subtracting by 1 inside the function. It's inside this cubed part. So that would be horizontal translation right C unit. Now, when we have multiple transformations happening here, this is when I think it's probably important to use this change to coordinate point business, that column on the table. So for the -1, that is, so translation right. And so what that does is, if you see on that column, we add that amount to our x value. If you look at the table on that column, it says f of x minus c, horizontal translation right, c units, and it says xy goes to x plus cy, so we add 1 to our x value. And then the other thing that we would do for this problem is we have this 1/8 here, so that is vertical compression, and that value, that 1/8, we multiply our y value by. So this is kind of like a code, a cheat code, to come up with our new coordinates. So for these more complex ones, I would recommend coming up with this coordinate code. For the ones where you're just translating left, right, up, and down, you might not necessarily need this. You could still use this for those. It works for those as well. But I think it's definitely important for these where things can get a little more confusing. So for this one, our origin, we want to shift it to the right. Our x value moves over 1. Our y value stays the same because 0 times 1/8 is still 0. So we want to shift it to the right 1 unit. But now we got to use these blue dots for the vertical compression. So that 1, 1 point is going to change to 2, and then 1 times 1/8 is 1/8. So that point is going to go down here to 1/8. Now, the thing is, I don't think it'll lock in at 1/8. And if it does, I don't know how we would even know that it's exactly 1/8. So that probably isn't going to be a good point for us to manipulate. We are probably going to want to manipulate this point right here, which our original point is 2, 8 for that one. So let's see where that one ends up. 2, 8. 2 plus 1 is 3, and then 8 times 1/8 is 1. So that is where that point ends up. So again, our green point moves over here, and then this blue point, this one, ends up at 3, 1. So let's go ahead and do that. And what's really nice about this is it makes sure that the other side matches, so we don't have to move that one as well. Let's go ahead and submit this. So we have multiply y coordinates by 1/8 and shift right 1 unit. And then the last type of problem here we have is just reflect functions. So remember, there's 2 types of reflections over the x-axis and over the y-axis. It's outside the function, like this one here is outside the function because it's not being cubed. That means it's a reflection over the y, or over the x-axis. Excuse me. If it's outside the function, it's a reflection over the x-axis. So like that. Right? The x-axis goes left to right. So if you reflect over that, you move up and down. So, and then let's see, here's one where the negative is inside the function. It's inside this cube root, so that is a reflection over the y-axis. So the y-axis goes up and down. So we want to reflect left to right in that case, right? So we're moving this is our y-axis, there's our x-axis. So we have this point right here is being reflected over the y-axis to here, right? So we get this new line going that way. If you have any questions on any of this, make sure you are asking for help during class, and have a good day.